Welcome to the lecture series on convolutional networks. This video covers MaxPooling as an inductive bias for images. So a modern neural network for image classification consists of several convolutional layers, could be 3, could be more, followed by standard neurons densely connected to each other, 1 or 2 or 3 layers, and finally the output units for the classification. Now each convolutional layer has several substages. The first stage is the convolutional stage, and this is essentially the filtering that we discussed in a previous video. Afterwards comes a rectified linear function or some other nonlinearity, and then comes the pooling stage. And the pooling stage is the topic of this video. So this would be one of these convolutional layers, and as I said, there are many of these. What I use here is the complex layer terminology. Each layer is complex. There's an alternative terminology that's also in use, the simple layer convolutional network terminology, where we would say the first convolutional layer is the filtering stage, the second one is the rectified linear unit, then the third one is the pooling layer. So that would count this as at least 2 different layers, whereas I count it in the following as one single layer. That's the complex layer terminology. So how does MaxPooling work? So here is a part of our image after the pre-processing by the filtering stage. And now we look at each segment of, say, 2 by 2, look for the maximum, and then we report this maximum as an output. Now, here is an example with stride 2. So we jump by 2 places, and then we look in this green area for the maximum. We report the maximum and put it down here. And then we continue at the yellow position and at the blue position. So this would be one filter, for example, the output of the filter number 17. This is this filter here. In total, we would, for example, have 64 filters, and after several pre-processing steps, we are now, say, at an image size of 224 times 224. The MaxPooling with stride 2 means that we essentially also have a downsampling, so that afterwards we still have the same number of filters, 64, but we are down at 112 times 112. So now let's repeat this, but use MaxPooling as before in a region 2.2, but with stride 1. So first we start in this reddish region, then we go one step further, we look for the maximum, we find the 7, we go one step further to the green region, we find again a 7. Then we go one step down in this region, the maximum would be the 6, we go one step to the right, the maximum is a 7, one step to the right, the maximum is a 7, one step down, one step to the right, one step to the right. So stride 1 has a nice property, which I would like to explain now. So suppose now we focus on this second filter position in the output. And now we imagine that the whole image is shifted by one step to the left. So I said we focus on this second filter position, which would correspond to this one here for the top filter, this one for the second filter, this one for the bottom filter. But now we imagine that we shift the image to the left. So essentially what would happen is that this moves one step further. So essentially the green region moves into the previous region where I have put the red rectangle. So what will happen is that whatever output was to the right of my red rectangle is now coming into the center. And this is shown on the next slide. So now I've shifted the image, and essentially at this second filter position, same position as before, we now have 773. Now, the previous entries were these. So you see that essentially in that second filter position, the entries have not changed. We have stability. The MaxPooling gives stability of the output of 2 out of the 3 here. Well, this one changed. It was 4 before, it's now a 3. But now imagine that instead of moving to the left, we would move the input image to the right, and something similar would happen. So MaxPooling has this inductive bias that says we have some sort of stability if we shift the image by a local transformation. A local shift, a local translation gives the same output for quite a few pixels. So quite a few of these activations remain the same when we wriggle the image one step to the left, and I promised we would also do it one step to the right. Let's do this now. This is back to the original position. Now I want to shift it one step to the right. So what would happen is that this 4 moves in, which means this remains the same. Now, for this direction, the other 2 positions would change. So not all of these entries are unchanged, but for each, be it a left shift or right shift, we can expect that many entries after the MaxPooling stage remain stable. Let's now apply this for specific tasks. So I have here 3 convolutional layers, 1, 2, 3, followed by a classifier, and we use the MNIST images, so we would have 10 outputs going from 0 to 9. Now, we work with MNIST images that have been padded by zeros, so instead of 28 times 28, they are now 40 times 40 of format, of size. Now, this is the complex layer terminology. A convolutional layer actually has 2 steps. It has a convolutional step and it has a MaxPooling step. The convolutional step is explained here. It's a convolution with a 3 times 3 filter. There's no padding. It's stride 2 and 2. So if we have a 40 times 40 image, we put it in here. What would come out at this stage is a 19 times 19. Then this is followed by the MaxPooling step. MaxPooling is again over region 2 by 2. We do padding of 0. We have a stride 1. So after this first complex convolutional layer, the output is 18 times 18, and we have chosen to use 32 filters. And now we repeat the same thing again. Convolution 3 times 3. We go up at the same time to 64 filters, and then we do it again MaxPooling 2 by 2 with stride 1, and the result of this is that the output here would be 7 times 7 times 64, and then we continue again in the same spirit, and the output would be 2 times 2 times 128. And then we go for classification. So now let's look what happens in terms of translation invariance. And this is shown on the right-hand side. We now take our image, the input image, 40 times 40, and we have different versions of it. We always stay in the 40 times 40 frames, but the actual image is shifted, for example, 5 pixels to the right, or 8 pixels to the right, or 5 pixels to the left. And now let's walk through the layers again. So this convolutional stage of the first convolutional layer is this greenish line, and you see that the sensitivity to a shifting is still very high. So what's plotted here is how much the activation of this layer, in that case layer 1 convolutional stage, changes if we shift the image, the 2 here, the pixel image, by a couple of pixels. And you see just a shift of 5 pixels changes the output completely. Now let's look at this gray line here, which is the output of the first convolutional layer, which means after the MaxPooling stage. And we see that actually we gain quite a bit of stability. We go from this greenish curve to the gray curve, and now the sensitivity to shifts has been reduced. That means we are more invariant to local translations of the image. Now the same thing repeats. So in step 3, we do another of these filtering stages. More or less nothing happens. But then when we do the MaxPooling, if you go to step number 4, then again we increase quite a bit. Now we go to the third layer, and let's look straight away at the output of this third convolutional layer. This is the dark red line up here, and you see it's very, very stable even against large shifts like 8 pixels. The output activity changes very little. So we have achieved not just a local translation invariance, but a translation invariance over large shifts of the image. The orange line at the very top is the activations of this next layer before we do any thresholding or softmax or maximization, which just an indication that further dense processing can stabilize against translations even further. So I made a point that MaxPooling is excellent to achieve local translation invariance. And then if we stack several of these convolutional layers, we go from a very local translation invariance to a near global translation invariance. So MaxPooling is great. Now, but not everybody thinks so. So this is a citation of Jeff Hinton, one of the founders of the field of deep neural networks. And he says the pooling operation used in convolutional networks is a big mistake. And the fact that it works so well is a disaster. Okay, why does he say this? Well, one reason is that maybe we don't want so much translation invariance, because somehow you forget where the object is. And if you have several objects on the scene on the same image, then completely forgetting the location of the image might not be good for all tasks. Now, let's look at citation of somebody else who did an empirical study, and we find that MaxPooling can simply be replaced by a convolutional layer with increased stride. And then if we do this, we find no loss in accuracy on several image recognition benchmarks. So maybe we don't need MaxPooling in practice. And here's the citation of the deep learning book of Goodfellow et al. There are other popular pooling functions, and such as averaging over a rectangular neighborhood, or even a weighted average would also work, essentially. Lots of people use it and also get good results. Now, I like a lot a paper that comes from a rigorous statistical framework, the framework of generative models. And in that paper, they say, we see that architectures and layer types commonly used in deep convolutional networks can be derived from precise probabilistic assumption. And that these assumptions entirely determine the network structure. So I think this is a very strong argument, and there's a whole family of papers that goes in that direction. That's not the only paper showing this, that there's this translation invariance in a statistical framework actually gives rise to MaxPooling. When I say translation invariance, I mean local translation invariance. So here is now again a standard deep convolutional network. You now know how to read this. So we start off with color images indicated by the little 3 here. 224 times 224, well, that's a small sized input image. And then this indicates that the filters that are used are 5 times 5 times 3. So the 3 for the color channels. And then this here indicates that we did a first convolutional stage, and how many filters are used in the first layer? Well, you just read it off here. So in that network structure, they use 64 filters. Then you can ask, why is the image size now 56 times 56? Well, they use these filters 5 times 5. So let's suppose that they have a stride of 2. And if they also use a padding of 2, that means they can start with putting the center of the filter in one of the corners and end up with the center of the filter in the other corner. And 224 divided by 4, the 4 comes from padding of, and the 4 now comes from a stride of 2 in both stages, the convolutional stage and the MaxPooling stage. So 224 divided by 4 gives 56. So that's what they used. And then it continues. Now it's 128 filters, and here it doesn't go down. They just do several of these stages. And finally, we have 2 layers of fully connected before we go to the actual classification, which seems to be here only 6 classes. So let's summarize. Convolutional networks exploit partial translation invariance of objects in images. Now, how do they exploit this? They exploit this by having an inductive bias. And the inductive bias is local translation invariance. And this is encoded in the network architecture in the form of these complex convolutional layers, where we have a filtering stage followed by a pooling stage. Well, pooling with stride 2 is often used to reduce dimensionality. However, in the simple example I have given, we see that pooling with stride 1 is more compatible with the idea of local translation invariance. Now, how can we then do dimensionality reduction? Well, it can be done by using strides larger than 1 in the convolutional filtering stage. So if you have a filter of the size 5.5, then you can easily use a stride of 2, and this allows dimensionality reduction. Then we have seen that MaxPooling can in practice be replaced by mean pooling, and people claim that in practice a pooling stage is not even necessary. So pooling has a foundation, MaxPooling has a foundation in local image transformation, invariance to local image translations, but in practice the specifics of the pooling stage don't matter, and you sometimes find that you don't even need it.